If we look around, most of us can see that nearly everything has color. Plastics, the leaves in trees, and especially paintings. But what allows for these fascinating colors to exist? The answer can be found where physics and chemistry collide in the science behind pigments. Each atom has a specific number of electrons that are arranged in orbitals around the atomic nucleus. The outermost electrons are called valence electrons, and the orbitals formed from these valence electrons play a huge role in color. Each section of the periodic table denotes a specific type of orbital that forms. These sections are the s block, the p block, the d block, and the f block. Since each atom has one more electron than the last, an electron in the s block will only have s orbitals in the valence shell. An electron in the p block will have both s and p orbitals in the valence shell. The d block is where things get weird. The valence shell does not have any d orbitals, but the shell below the valence shell does. However, this d orbital does not have to be full before the p orbital is. In addition, the atom loses the electrons in its valence shell and an ion forms, meaning that the d block is now in the valence shell. This means that the d orbital of the metal atoms can have empty spaces. When ions or ionic compounds, called ligands, approach a metal ion, they cause the d orbital in the valence shell of the metal ion to split into both a higher energy d orbital and a lower energy d orbital. The energy difference between these two d orbitals corresponds to the energy of a specific wavelength of light, where energy equals Planck's constant times the speed of light divided by wavelength, because that is the energy required to remove an electron from a lower to a higher energy d orbital. This is the light wavelength absorbed by the pigment, and if we look at a color wheel, the opposite color from the one absorbed is what we see. These types of pigments are formed because of the energy associated with D to D transitions, but the colors formed are not as bright as the colors formed with other types of pigments. In ligand to metal charge transfer, or LMCT pigments, an electron jumps from the orbital of a ligand to the d orbital of a metal ion. The opposite of this is metal to ligand charge transfer pigments, where the electron jumps from the metal to the ligand. Just like in D to D transitions, the energy required for the electron to make this jump corresponds to a wavelength that is absorbed by the pigment. If we look at a color wheel, the opposite color as the color absorbed will be what the observer sees. Ligand to metal charge transfer and metal to ligand charge transfer pigments, however, are much different from D to D transition pigments in that they produce much brighter colors, which expands the amount of pigments that we have to use in cosmetics, plastics, and of course, paints.